Okay. Yeah.
Can you number 51 and 311?
Yeah. Oh yeah, so this is the classic place where the stuff is used. Telephone line hangs between two poles of 14 meters apart. This is number 51, page 263. This one here, right?
Yeah.
Okay. Because they want to get like halfway through the problem. I didn't mean that one. So it hangs, this telephone wire hangs between those. There. So they actually, they set up, part of this problem normally would be to set up your own coordinate system, but they kind of do it for us. Not a bad idea to put the origin right in the middle. Let's see. Blah, 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 blah. So then why they give us the formula for this shape here, put it up here, y equals minus 15, okay, cool. And they give us, so right at 0, this thing is going to be 5. They give us that value right there, 5. And you can kind of see that. Cosh of 0, I don't know if you guys remember how cosh is defined. It's e to the x minus. So if at 0, this is going to be 0. At 0, this is going to be, should be 1. So e to the x plus e to the 1 plus 1 over 2, that would be 1. 20 minus 15 is 5. So that's why this height here is 5. Find this, okay, this is a good problem. Find the slope of this curve where it meets the right pole. So we want to know the slope when it meets this pole. We want to know the slope right there. So that's part A. So, how would you do that part? Part A. How do you find the slope at any point on any function?
Derivative.
Yeah, take the derivative. All right. And we know the derivative of cosh. You don't have to memorize it, but you know what it is. Yeah. So, y prime, this is for part A. And of course, just because we learn a new function doesn't mean that any of the old rules have to change. They don't care. The old rules are just always there. They're always behind. So I have some function that's new to me, but I don't care. Inside here I have some function of x. So what rule is going to have to come into play? Chain rule. So when I do this, I get 20 sinh x over 20, but then what's the derivative of the inside?
1 over 20.
Yeah. So that goes away. That's nice. That's cool. And of course, minus 15, that goes away. And I want to know the derivative of this at 7. So just have to plug in 7 and see what comes out. And on your graphing calculators, we looked at it, that catalog button kicks ass. Because it has everything your calculator can do. If you have a scientific calculator, it's actually most often easier to get these. Very often there'll be like a height button. And you'll push that, and then you'll push the sign, so it makes the hyperbolic sign.
357.
Oh, so whatever it is, 357? Okay. 0.357?
Yeah.
Okay. Okay with that. Okay, so everybody can verify that. I'm going off of blind optimism and faith.
How would you do it on the scientific calculator?
On many scientifics, they have height. But there it is. So second height, I think normally it's normally second height and then hit sine or cosine or whatever. In our graphing calculator, the only way I can figure out how to get there is to go second 0 to catalog and to pick the one you want. If you figure out another way, I always forget to look it up. And it really just doesn't come up very often. So, all right, and then part B might be the one where we really want to find out what the hell's going on. Find the angle theta between the line and the pole. So now I want to know this angle here. Now somehow part A is going to help me with part B because I really want you to understand here. this slope, the slope at that point. So I've drawn the tangent line. So that means that this tangent line has a slope everywhere of what? 0.357, yeah, of course, because that's the definition of the tangent line. That's the slope of the tangent line. So everywhere I've drawn that. So now I've got, let's focus on this little triangle here. And I think I've got theta in the right place, right? Yeah. They don't really make it very clear, but I think that's what they mean. So I want to find that angle. Since this is 0.357, what sides of the triangle do I know? Or can I specify? It doesn't matter how big you make this triangle, because the ratios always have to come out the same. But you got to be careful now. What is this? Yeah, so you got there a little bit ahead of me, but let's kind of take it step by step, and then we'll see why it comes out to be that.
Oh, sine over your cosine? Do like that over 1 maybe? And then do your right side and your
So if this has got a slope of 0.357, that means that this and this, the ratio of those two sides must be 0.357, right? And of course the ratio of those two sides is the tangent. So then I know that the tangent of theta has to be 0.357. Now, is that, you guys kind of with me?
Yeah.
That's really cool. That is something that's not that big of a stretch from pre-calculus and calculus, but it's something you don't learn directly necessarily. It's kind of cool. It's the slope as it relates to a triangle I can make off of it. You don't really see a problem like that too often, but to tell you honestly, you use that kind of thing more often than you see it in class. Yeah.
What'd you get for the bottom side of that triangle? You said 357,
It's
right?
3.57
Doesn't matter.
over 1.
All that really matters is that this ratio is 0.357.
Okay.
So you could actually define this to be, bless you. Don't define it to be bless you, I don't know what kind of problem. 0.357 to 1. Or whatever else numbers make it 0.357 at the end. Of course, I'm going to pick that. But the really nice thing, like you said, that ratio is defined to be tangent theta. And then how do you figure out theta? Arctangent, inverse tangent, however you want to call it.
Professor, about
Yes.
the theta is 1 over 0.3. Should be theta this one?
Oh yeah, thank you. I keep thinking about this. Since this base is over here, this should be that. Cool. Thank you. Because the angle is on the upside. So my y and my x have been reversed. That's beautiful. So it doesn't change the fact that this ratio has to be 0.357. I should have set it equal to maybe cotangent theta. That would have been fine. Because my angle is not in the base. So if you learn SOHCAHTOA, that's the only trig place you'll have a little bit easier time than I do. Everything else is easier for me. Yeah. All right, cool. That one's a little freaky when you first read it. You're like, how the hell do I know that? Yeah.
What did theta come out to be for you?
I don't know. What's arctangent of that? Yeah.
1.23.
Yeah, 1.23 what? I don't know, whatever mode you're in. That should probably be radians, right? Yeah. Cool.
Professor, I understand all the steps you take here except for that one when you took the derivative of y, it looks like. Is it 20 divided by 20?
Oh yeah, because I did a little reorganization on the fly. Because this would be times the derivative of the inside.
Mm-hmm.
And what's the derivative of 1/20th x?
120.
1/20th.
Oh.
Yeah, and so those 20s will, wherever they are, they'll kill each other.
Gotcha.
Yeah. I will find you. Yeah.
There's another one for 4.1.
Yeah, sure.
Number
You
45.
got the floor, dude. Nobody else is asking.
Number 45. I put that in the graphing calculator and I saw that it crossed the x-axis several times, but the answer for it in the back of the book was the number of critical values is 10, but it looks like a sine function just goes on forever.
Mm-hmm.
How do you get 10?
So let's see. So this one does call for you to put it into the calculator. You're alive. Let's take a look at what this thing looks like. Okay. So, what kind of function is that? We talked about that kind of thing before. What's going on with that function? This is
Like a pendulum?
number 45, page 281. Say again.
Like a pendulum?
In what way?
Decreases in amplitude?
I like it. So it's decreasing in amplitude. So there's a lot of things. Pendulum is one example, right? Where over time you'll decrease in amplitude. Or it could be, we talked about plucking a string on a guitar or something. Thankfully, they eventually die out. Or else we'd all be dead already from just too much noise. Pluck that string. Someday this will come on. So let's see what this thing looks like now. Okay. Oh, and your absolute value symbol, I think it's under math. I'll find
Yeah, it
out
is.
together. Cool. So put this thing in there. I need there's a floor and the ceiling from before. So we got 5. Yeah. So the -0.1 absolute value of x.
So right. So under number. Yeah.
Look at that. That's awesome. Sorry, I'm still liking the new
Notation fast.
yeah, the whole thing is new updated stuff for the calculator. Alright, so let's see. Oh yeah, so I know I had a good idea that my window was freaky. Oh, I freaked it way too far out. Alright, let's go back in there.
This is 32.
This is number 45.
141.
Please be in there. Thank God. Okay. Zoom 6. Alright, so there's that bad boy going there. Cool, man. The trick here is the -1 part. If I go out far enough, so if you don't go out far enough, you might make the mistake that this thing's going to continuously. But what's going on here is, this is a sine function that is not a normal sine function. This sine function is going to decrease in both directions. So I'm just going to focus in one direction. But it's been shifted down by what?
-1.
By what?
Right? So it's got an amplitude of 5, but it's been shifted down by 1. So eventually it's not going to be able to go back up to 0 again. It's going to be such a small, its amplitude over time is decreasing. So if I go out far enough, it's been -20 to 20.
Why
So
does the -1 cause this? Or
E to a negative power. In fact, it's either e to the negative x squared or e to the negative absolute value of x there, like they have here. Which means normally e to the negative x, just here's your normal, see from your perspective, it would look like this. That's the normal e to the x, right? So of course e to the negative x would just be like this. But if I do e to the negative absolute value of x, it would look like that.
Okay.
Right? It's going to look like that. The positive values of x on both sides. You with me? So it's got like a maximum there in the middle. So what I've done is I'm pushing down on my sine function in both directions, actually. Right? Its amplitude it starts off at 5, but then as I let x get bigger, I'm pushing down on the amplitude. Now it's been pushed down by 1. So if the amplitude ever gets to be below 1, it's not going to be able to hit. And of course the amplitude is going to go down below 1 because I keep pushing forever. Each of the negative is going to keep going closer and closer to 0. So I just have to look out far enough. And I can kind of blow it up a little bit too. Let's see.
Did you say e to the absolute value of x, or did you say
Negative. You do negative absolute, yeah. Or you do negative x squared. Both of those kind of accomplish the same thing. So that it goes down in both directions. Cool. Let me see. Let me make this a little bit smaller. All right, let's take a look here. There, back there. See, poor little dude.
Oh, yeah, it doesn't cross the domain.
But it's because of that -1. That's the part that does it. If they didn't have the -1 in there, I agree, it would go across it infinitely many times. But the minute they push it down by 1, if its amplitude gets below 1, he can't reach the x-axis anymore.
So is that, let me count right now, is that equal to 10?
I don't know. 1, 2, 3, 4, 5, 6, 7, 8, and then 9 and 10. Those two at the ends must be singular. Must hit it just once.
I got you.
Yeah.
Cool.
I like it.
Cool T.
Yes.
Can you explain to us tangent theta equals 1/point?
All right. So there's a couple things going on there. First off, this has a slope. This line has a slope of 0.357, which means, of course, slope is change in x under change in y, right? Just to say that in a very strange way. So then I know that whatever the hell these are, however big I happen to make my triangle, these have got to reduce to be 0.357, right? Okay, cool. So then I can make this 0.357, I can make that 1.
All right.
I like it. And then just because this angle is here instead of here, well, here instead of here, I've got to use cotangent, because now it's going to be either use cotangent or use 1 over that. So this could be cotangent theta equals 0.357.
Okay.
Because my angle's there. So for me, I'd have to look at it like that. Right?
Yeah.
Or for the SOHCAHTOA people, you don't have to.
Then we have to do the whole arctangent thing, and we're good, right?
What's that?
We have to do the whole arctangent thing, and we're good.
Exactly. Okay. So those two are good. That one's not too bad as long as you go out far enough.
So if you don't have a graphic calculator, you got screwed.
Little tiny bit. Wait. If you set, you could set that equal to 0 and try to solve by hand. I would not. You recommend that? I would not recommend that. You could do it.
Could you do number 9 on
You could,
3.10?
really. What?
Number 9 on 3.10.
Oh, cool. Okay, good. All right, that makes sense. Because there was a question somebody asked at the end of class after we talked about linear approximations. Because some of the examples we did in class were a little bit too simplified, to be honest. So in the homework, you're going to see something more complicated. It's like number 9. It says, verify the given linear approximation at a equals 0. Okay, so you know that a equals 0. That's the point we're kind of expanding around, right? That's the language I use. Weird language. You're going to make a line that approximates the function near 0. That's another way to say it. And the function we're working with is this dude. So just don't forget that. It's, to be completely honest, let's do this 2 ways. Find the tangent. Find the equation of the tangent line. Let's do this like an old style problem. Find the equation of the tangent line to f of x. Jeff, you can write. Yeah. To f of x at x equals to 0. Cool. Just that a is like c in the mean value theorem. When I was a student, I just always used x. I said, screw it. I know I mean a specific value, but they just want to say that's a specific value, whatever. This is old school. This is old news. This is what we were doing like way back when we first learned the derivative rule for this. But I want to show you how it's the same damn thing we're doing here. If you just find the equation of the tangent line, you're golden. So you don't, well, we'll do it both ways. So what's the first step to find the equation of this tangent line?
Take the derivative.
Yeah, take the derivative. So let me write that like this. It's a little better.
It's negative.
What's f prime?
Quarter
Good.
1 over 1/4
Quarter.
minus, or the inside, which is 1 plus 2x
times 2.
times to the negative 3/4
Good.
times 2.
Good. Times the 2 from the inside. That's the chain rule. Okay. And of course, I need to know my slope. My slope will be f prime at 0. So what's my slope going to be?
One.
You said it's 2 times 1/4.
1.
This is together with
Yeah, it'll be 1/4 times 1 times 2.
So it's 1/2.
1/2. All right. Sweet. So far, so good.
However, that's here. Oh, okay.
Now, how do I get the rest of my equation? My mx plus b.
Point slope intercept.
You put it.
Yeah, whatever way you want to do it. What's my point that I'm working with, though? 0,
0, 1.
1. That's crazy. Right. So if I know that, so I have y equals 1/2 x plus. What do I put there to make it at 0? I need it to be 1. Yeah, that's the y-intercept. So 1. You guys kind of with me? Now look at what the actual answer is supposed to be.
How's it 1?
1/2 x plus 1. Say again?
How's it 1?
This is beautiful because that's automatically my y-intercept, which is my b,
Okay.
right?
Yeah.
It's really funny how some of the simplest stuff will come back up and be a part of this complicated problem. So if you have the y-intercept, oh sweet, I can just plug it in. Don't do all this other work. The official way to do it, which, again, the reason that you want to look at it like this is what this section says. And again, this is just, that's all it is, right? Just written in more general terms. Now that we know calculus, we know a more general way to find slope. It's better to know it in that form, even though it's the same damn thing as this, because in proofs, in fact, in a proof we're going to work with today, this might come up a little bit, knowing how to rewrite f of x in general near some other thing, because when we deal with limits near, we're getting really close to a value, like close to a. Well, really close to a, f of x is this. So I can just substitute that in. Kicks ass. Okay. So then if you plug this stuff in, we already got all the work. So f prime at 0 is 1/2. A is 0. F of a is 1. So there's your 1/2 x plus 1. How we doing? Same thing both ways. Doesn't matter. So it's old news, just kind of recast in a slightly different look. But it's just using y minus y1, blah, blah, blah. Okay, good. So that's part A. Part B says, determine the values of x for which the linear approximation is accurate to within 0.1. All right. This is normally the part people really, really enjoy. So I want this guy. This is on page. We did a couple of these last time, but they kind of run through the. Well, so example on page 252. Well, they kind of run through it. But basically, I can cut to the chase and say, I want this approximation. No, it's not really squeeze through.
But the
Yeah. 4 through to that minus 0.1 and the 4 through to that plus 0.1. So I want it to be within 0.1 of the actual function. I want to know how wide of an interval is that true for? And that's where you just plot it. This is what I was calling this the floor, the function, and the ceiling. You want to see which one it hits. Normally it hits one a couple times. For some functions it might hit both, but you just got to deal with it.
Also, if you don't have a calculator, you can have
What's up?
that. Also, if you don't have a calculator, you can have that.
Can you do with the exact value though? You like take your F of A plus 0.1 or something? Alright, can you take the difference between the actual number and your
No, because I need x to be left open because that's what I'm trying to determine. It's not at a specific point. I want to know actually which x values would this be within 0.1 of this.
I think I'm thinking of a different problem.
Probably.
So how do you do that?
I don't know if you guys want to see this again, but you put in the floor. 1 plus 2x to the 1/4. You put in our oops, the floor is minus 0.1 from that. Okay, minus 0.1.
Why here 1/2 x plus 1?
Yeah, that's going to be in the middle. So I'm putting that in first.
So why 1/2 x plus 1?
It's the derivative.
Why is it?
Here, the last equation.
Oh, because the y-intercept is 1. So at x equal to 0, y is 1. Right, because that's the point that we have to go through. So I want to know at x equal to 0. So at x equal to 0, what's the value of this function? It's 1. So this line has to go at 0. It's got to go through 1.
We didn't substitute in x0?
Yes.
0, 1?
Beautiful. Just plug a 0 in there, and I get 1 to the whatever is 1. Cool. So I got my ceiling, my floor. Yes, sir.
Just want to check, when you say accurate to the plus or minus 0.1, or, I guess 1/10, you just pick that number because, right, you didn't get it?
I didn't pick it. It was given to me
Oh, in the equation?
in the problem, yeah.
Okay.
They have to tell you how close they want you to be.
Okay, yeah, that's what I was wondering. All
In the
right.
real world, it's a question of, it could be a tolerance of a piece you're trying to fit in somewhere, and the machine is okay within so much, or a tolerance of variation in your energy you're putting into something.
Gotcha.
So it's kind of determined by not blowing anything up sometimes, right?
Okay.
And the problems are going to be whatever the hell they feel like making it to you.
Gotcha, okay.
Do I speak from experience? Yes. So I graph this thing. There's my floor. There's my approximation. There's my ceiling. And now I can see where to do my zoom box, right? I don't know if we did this enough the other day. So very, very quickly. There's my floor. Because my approximation, so it doesn't touch the floor at all. And here's my ceiling, and it touches the ceiling at 2 places, so I can find what values of x does it live within there. So within this band, I hope you understand the actual function values will be right in the middle of these two, of course, right? Because that's minus 0.1, that's plus 0.1. Are you guys with me? So I want to know, where does this function, this approximation, that's the straight line approximation, when is it within this? And that's really just finding when does it hit there, when does it hit there. That's why that problem just becomes finding intersections.
Will you always get a secant line in one of these types of problems? Linear approximation problems?
Like I said, it depends on the kind of function we're seeing. It might hit both the ceiling and the floor, but most often it hits just one or the other twice. Yeah. Okay. Cool. Possibly, or not at all, or... Yeah.
On 4.1, do we do, actually, no, not 4.1, sorry. 3.10, can we do number 6? You got halfway through and I just got stuck.
Oh, good. All right, good. This is the other part of what I was talking about earlier. Number 6. So they give you this function there. So find the linear approximation at a equal to 0 and use it to approximate cube root of 0.95, cube root of 1.1, blah, 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 right? So, whichever way you like better, you can either just treat this as an old problem, say find the tangent line. That will be the linear approximation. Or you can kind of put it, I kind of would like it if you guys did it this way, but it really doesn't matter to me too much. Let's just get you used to the form of it, because it will come up every now and again. So what's f of 0?
1.
1. What's f prime of x?
0.
1/3 times.
Careful. So there's f of x. What's f prime of x?
1/3
Yeah.
times 1 plus x raised to the negative 2/3.
Good. Times 1. I love it. So what's f prime of 0?
1/3.
1/3. So then I get f of x is approximately 1 plus 1/3 of x minus 0. So 1/3 x. Okay, so this is very much like the problem we just did. Right, so it's just got a different root on this thing. And then, so the interesting part is this part here. Because you have to remember what the function itself is. So, I know my approximation is 1 plus 1/3 x, but x is not 0.95. It is so desperately not 0.95. Because if I make x 0.95, what am I actually calculating? The cube root of 1.95. Shit. So you got to figure out what would you make x so that you get this inside.
Negative 0.5.
Yeah, so you figure out that f of negative 0.05 would be the cube root of 0.95. Is that cool? There, now you can use this approximation to figure out what that is.
This is supposed to.
You guys see what I'm saying? That's the part that we didn't see the other day. We didn't see something that had a lot of, or anything going on inside, really. This is not going to be x. This is what you want the input to be. You have to figure out what x has to be to make that happen. So, of course, if I just had an x in there, the input would be 0.95. Ooh, bless you. That's all right. But now to make it 0.95 inside, I have to make it negative 0.05 for the value. So now when I want to go to approximate it, f of negative 0.05 is approximately
1 plus negative 0.05 over 3.
Yeah, 1 plus 1/3 and negative 0.05. Cool. And whatever the hell that is. Yeah.
So you have two lines to where it would be plus 0.1 for the other one?
No. So this problem is the other thing you could do. With linear approximations, you could either figure out with tolerance where you are within so much, or you could use them to figure out concrete values. You could figure out approximations to concrete values. This is not asking me to figure out some tolerance. When is it off by 0.1? This is just saying, find an approximation for this. So if once I do this, I'm done with that part. For 1.1, x would be, I didn't make 1.1 there, you made x 0.1. It's crazy. So then f of 1.1 is approximately 1 plus 1/3 times 0.1. That's what x has to be. You guys see what you got to be careful about. Because that kind of thing might come up on a quiz or a test. Yeah.
So on the thing where you have f of negative 0.05 is equal to the cube root of 0.95. And then underneath you wrote f of negative 0.05 is roughly equal to 1 plus 1/3 minus 0.05. How do you do?
So is this cool up here? Is this cool, this fact?
Yes.
Right? Good. So if I want to know the approximate value of this, I let x be this in my approximation.
Okay. All right.
Cool. It's because that 1 plus, I can't just put this in, 0.95, I can't just plug it there. I have to figure out what is x actually equal to make 0.95 inside. That's the x value I have to plug into my approximation. That's the actual x value. F of 2 is not cube root of 2. F of 2 is cube root of 3.
Yeah.
Thank you. Right, so you have to be careful. If I want 0.95, it's not f of 0.95. It's f of negative 0.05. Okay, maybe. So let's investigate it. What is 1 plus 1/3 of that.
0.98.
0.98.
I think so, I don't know.
I got 5960. It's just probably the same thing.
Yeah, 0.983.
0.9833. Now somebody help me out. What's the cube root of 0.95?
Roughly the same thing.
That's a really good guess.
I don't know. I can't do cube
I
roots.
can't fault you for
I
that.
can't do cube roots in my mind.
Kind of happy I can't. I don't know what I would have to lose to be able to do that. So the cube root of 0.95. 0.983. Cool, man. So I mean, we could, and in fact, you can imagine. I can't give you several of all the different kinds. So I'll probably do a problem where I have you find a linear approximation. Have you tell me how far can you go, and it's still good to within whatever. And then I'll have you do something like this, all in the same problem. I don't think the homework really does that. They do one of two things. They either you find it and you use it, or you find it and you figure out the limits, the tolerance. You guys got it?
Which one would be coming first, though? Would you want us to do B and then what you did, or would you?
Oh, it doesn't matter. They're independent of each other to a point, right? I mean, considering that this came out so damn close, then I know that that 0.05 away is not that far relatively. You guys kind of with me? The value is still pretty close. So 0.1 would be the next thing. If I go 0.1, is that getting pretty far away? I don't know. Okay. How you doing with that? Is that semi-decent? You guys see that? Yes, sir.
There was a problem like this. I was dealing with, I believe, let's see, max error, relative error, percentage error. Is that important? It was a volume kind of thing, and said he used differentials or something. It was
Yeah, the differentials.
33 on 310.
That's the question I'm waiting for, because I didn't talk about differentials when we went through this section. I kind of left it up to you to read about. 33.
Kind of assumed it meant derivatives. I didn't really know.
The edge of a cube is found to be 30 centimeters with a possible error in measurement of 0.1 centimeters.
Edge of the cube.
Yeah. Use differentials to estimate the maximum possible error, relative error, percentage error, blah, 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 blah. So the volume of the cube, in general, would be
30 cubes. Oh, x cubed.
x cubed, in general, right? So to find the error, you could use differentials. And what differentials are, they're almost kind of too silly. But they have a really good picture of it.
Did you say 260?
Yes.
Okay.
Let me show you why. I mean, it's really, I'm hoping you guys are at least attempting to read through the book here.
They look really similar to the dy.
Okay. So this picture, let's focus on this picture here. There you go, good. So let me see how they got this up. From that figure 5. Here we go. Okay. Okay, good. So this red line is most likely how related to this blue line.
The tangent line.
Good, and it is. Good. So this red line is the tangent line to this blue line. So this kind of contains some of this idea about how far can we get away from the A value and still be good, within so much. I don't want to be off by too much. And you can see what's happening. The blue line, of course, is curving, but my tangent line is not going to curve. It's only going to hug it for a little while. So if I change my x by so much, and my dx and my delta x are the same.
Makes sense.
No, we know so far. Because the amount that x changes is the same. I don't care which line I'm looking at. That's why those two are the same. How we doing? The red line and the blue line? Who cares? But of course, the change in the value is going to be different for the two. Delta y is the actual change. Delta y is always the actual change. dy is the predicted change from the tangent line. And of course, if you go too far out, you're going to be way far off. Right? So that's the whole point of how far can I go and still be good to within so much. How are you guys doing so far? So this picture and this idea of differentials kind of captures a lot of what we're talking about with the linear approximations. Okay. So it's kind of hidden there, but I know that dy is going to be f prime of x. Well, in fact, you can imagine how to figure out how much it changes. If I have a straight line, and I know it's so much here, how much will it change by a little bit later? If the slope, so if at a it's 1, let's not say a. At 1 it's 1, and I want to know at 2 what's it going to be, and I'll tell you the slope is 3. Can you figure that out? How much is it going to change by? It's going to change by 3. It's kind of silly. So the dy, the amount that this changes by, is going to be equal to f prime times dx. Now, in a sense, this works so often, and it's difficult to accept that dy and dx are not truly separate. And in fact, a lot of people, me included, think that they can be looked at like that anyway. But if I divide by dx, isn't that just f prime equals dy dx? And don't we already know that?
Yeah.
So that's one level of why this is almost silly. But it's not trivial because dx is not truly its own thing that you can just... The ratio matters here. But what we're saying is if you look at it like this, then this does make sense. The amount that y changes related to the tangent line is equal to this. We just know it is. Of course, we've known that since algebra. I'm not going to show this to my algebra class, but they know this. They just don't know what it looks like. So what is it? Oh, yeah.
Well, what's the difference between dy by itself compared to dy dx?
You mean, well, this is purely, this by itself is just how much y changes.
Okay.
The change in y, and this is really just,
Isn't it dependent off of the change in x?
of course, and this is exactly what it says.
Yeah.
So it's just a different way of saying the same thing, the ratio. The amount that y changes is some multiple of the amount that x changes. And that's actually like a definition of slope. But when I first introduce slope to people, I call it the amplifier. Right? Whatever x does, it amplifies, it makes y do. And of course, sometimes it shrinks it, but oh well. So we figure it out.
But because it's dx, it's not delta x, does that mean it's a bigger change?
The funny thing here is,
though it does not matter because it says that
the reason it's dx is because this is the one that's determined by calculus.
Yes.
Yes. And the funny thing here, of course, is that delta y is actually the more accurate one. Because in this case, calculus is being used to approximate something. So this is kind of reversed. We normally think of calculus as being the more precise way, well, like we did with secant line. No secant line can ever be as good as the actual f prime at that point, right? But since we're using calculus to approximate, in this case, delta y is, of course, the accurate thing. That's how much y changed. My calculus approximation is always going to be off, but we're cool with that because it's a freaking approximation. Who cares? Right? And I've made a line out of a curve. What more do you want?
So,
but you're right.
So could you change the d to a delta? And would it affect anything?
No, for this one?
For either or
Not
both?
for this one. Because this officially is how much y actually changes.
Whereas it's more of an approximation.
This is how much the tangent line changes. Since delta x equals dx, you could interchange that, but you just normally don't, just to keep the calc stuff all together. All right, cool. How have we done so far? So on one level, it sounds like it's really difficult. You know what the hell to do with this stuff. But on another level, it's almost too simple. It's stuff we've already kind of known. It's just playing around with stuff we've known from before. Now, what's the thing you say? Oh, yeah, we get the volume. So what's the volume of the cube? Is x cubed?
Yeah.
So if I want to approximate, and they ask me for relative change. Yes, sir.
I'm just looking at this, before I even got started on this, I was thinking, why do they give you a change when you could calculate the volume plus or minus the 0.1 without calculus? You get 30.1, the volume of that compared to the 30 cubed?
Because you want to compare, the point they're trying to make is that doing the actual work by changing all the signs by 0.1
Yeah.
versus approximating it with calculus, right? It's always a question of how precise do you need to be. So calculus is an awesome approximation tool, and in Calc 2 you learn how to make those approximations better. I call those Taylor polynomials, right? Where you go to higher level derivatives to make it more and more precise. You don't let it be a straight line, tangent line. You actually have a tangent curve, which gets neat. Like, great. But what would dv, using this rule for differentials, dv would equal what?
3x squared.
3x squared dx. And dx
Is that
is 0.1, right?
absolute value? Or just point?
Just 0.1. That's how much x is going to be changed by. Because I think it said specifically, I know I put plus or minus, but please. Oh, it's just the error measurement, 0.1. Okay. No, it will still be 0.1. So if I wanted to approximate the change in volume, then I can say dv equals 3, what's x? 30. That's what is at the point that I'm interested in. And of course, dx, 0.1. And that works in both directions. If I could put a negative in there, it would still be the same number. It just tells me if I am off by negative 0.1, it would just volume would change by negative this number. And that's I think what you meant by absolute value, but plus or minus that.
Is that a coincidence because of the thing? Because, like, when I think about shapes like this, I feel like as they get bigger, you get bigger growth. I don't know, am I wrong in that? So that's what I think of. Like surface
Well,
area?
the growth in general, the if you look at this, the growth in volume is always going to be this many times as big as the growth in the side length. So, and this is not a related rates problem. It doesn't have to do anything to do with how quickly this is happening.
Yeah.
But this is always going to be some multiple, and this multiple is only getting bigger. As this changes, gets bigger, right?
So, okay, so the dx is making up for the... I don't know, okay.
So,
Well, if you make this too big, then your straight line approximations get too far away, and this is definitely going to be a curve, right? So you can't make this too big. But you can then say, okay, now I'm at 30.1. Now let me change things. Now I'm at 30.2. Now let me change things. I can't stay at 30 and plop this on to 100. I have to change this number and then plop on something. Does that make sense? So my approximation for how much the volume is changing is about...
so you have 2700 times the 0.1.
Cool. 270 cubic centimeters. So if you do it the other way, then you actually have to change it 29, 29, 29 to get a lower bound, and then 31, 31, 31. So what do you get to what's 29 cubed?
30.1.
30.1, yeah.
Or you can just do
29.9.
Yeah.
And 30.1. And see what the difference is there. And of course in the middle you got your 30. So I know 30 cubed was 29.9 cubes. Somebody help me out.
2.67 times 10 to the 4th.
10 to the 4th?
Oh,
Oh, this is too small.
yeah, I would say just put that.
Yeah.
with a zero.
Yeah, thank you.
29.29 cubes.
And then what's, say again? 30.1 cube?
Do you want the exact numbers, or are you rounding out?
2.73 times 10 to the 4th. Sorry, it's scientific.
So it's off by,
I got actually 27,270. So it actually was 270.
it is 270?
270.9.
I like you better.
It's very close.
And then that one's probably something else, but okay.
Yeah.
So that's the actual, that's kind of like the actual change in this volume. This is the estimated change, and they actually come out to be pretty good. Of course, the smaller this is, the better it's going to be, and that relates to getting closer and closer, so the straight line is better and better. The curve has less chance to get away from it if I zoom in closer and closer.
So DD is basically just a change
Change in volume. Good.
based on the granted, if we had a much number at the error bar.
So the maximum possible error. Relative error is just take the error divided by your volume.
Which volume here? 30 volume or?
Yeah, they got an example there on page, here, I'll show you. I'm not overly worried about this, is not going to show up anywhere, just want you guys to do a problem like this, but there's your relative error.
So we want there to be different types of error and stuff on the test.
Probably not. We'll see. I'm more interested in the linear approximations from this section. But the differentials are going to come up later.
Okay.
Again, a little bit, not the same way. Okay. Okay. So anything else from the homework?
Number 63, 4-1.
4-1? Oh yeah, good. I like this problem. That was dramatic. What was that? If A and B are positive numbers, find the maximum value. Of yeah. Like that. Yep. So A and B are positive.
What section is this? 3.10?
It's 4-1.
4.1, yeah. So of course, how do you find the maximum value of any function?
You find the root of the derivative.
Yeah, good. So you take the derivative and then find out where that equals 0. That's the first step, right? So get the critical numbers for this, right? So what's the derivative of this?
ax to the a minus 1 minus x b, and then minus b.
I got you. I understand.
Plus b x to the a 1 minus x b minus 1. And then because the negative 1 becomes negative.
I like it. So there's a chain rule there. Cool. Okay, so factor that bad boy. And this is I like this problem. You can see why I like this problem. What's the smallest exponent on x?
To the a minus 1.
X to the a minus 1. So I can take out an x to the a minus 1, and I can take out how many of these? Minus 1, the smaller exponent, right? Always take out the smallest exponent. We saw an example yesterday with negatives. That always freaks people out.
A
Yeah?
1 minus x minus bx.
Yeah, minus thing. So I get x to the a minus 1, 1 minus x to the b minus 1, and then I get a minus, let's see, how do I want to put this? A plus b x. Why not? I'll let you guys chew on that for a second. So this is a restricted domain problem, right? So the only place where the maximum value could possibly occur would be at the endpoints or critical values, as long as the critical values are within that interval. Is that cool?
How do you get that bottom piece, the minus a plus bx?
So this would be a minus ax minus bx. So just take out a negative x from there. Yeah, cool. You don't have to do that. Doesn't really matter, but it just makes the next step easier. Okay, so what are the critical numbers for this? Yeah, x equal to 0. And of course, those are where, there's a couple things. That's where the function is. What's the function of those values? If x is 0, f is 0. If x is 1, f is 0. Cool, right? So that makes the function 0. And it's the endpoints. So I know that f at 0 and f at 1 are both 0. Right? Doesn't really tell me anything yet, because that could be the biggest value. Who knows? And what's the last possible critical number I have? Because you can't forget this poor little dude.
It's A plus B over A.
Yeah, be careful. It'd be A equals A plus B x, right?
Would it be A minus B?
Nope. Take a negative out.
A
That's
over
plus.
A plus B.
A over A plus B. Okay. Is that between 0 and 1?
What's that A and B?
A and B are both positive. So A plus B relative to A. A plus B must be
C.
bigger than A, right? So this is a proper fraction. It's between 0 and 1 by definition. You know, let that sink in. You see, this is, there are several problems in each section that if nobody asks me a question before the test, I get very worried about if homework is being done. This is a weird-ass question. If I don't get this question, I'm like, what the hell's going on? I expect this question. So how do you check to see if this thing is...
Number line.
Yeah, you could do the number line. Well, even better than that, you don't have to do that. This is a restricted domain problem. This is purely like an absolute extreme, absolute. Right? I checked the endpoints already. All I have to do is check this. Plug it in. Gross. But the beautiful thing, I want you to realize, as long as it's not 0, as long as it's positive and not 0, it's the maximum value. Do you understand? The question says, find the maximum value. Oh, I like it. It's even better than I thought. So, when you plug this in, will it make this 0?
Maybe.
Oh, hell no. Please tell me why not. What things make this 0? 0 and 1. Is that either of those? No. How are we doing? Because A and B are both positive. So that can't be 0. And it can't be 1. Because A can't be equal to A plus B. How you doing? Do you understand? So this does not make this 0. So at least it's not 0. Okay, hold on. Every time I turn around, you look at me the same way. It's freaking me out. All right. God, I just hope to God you guys are starting to understand. The reason I love this kind of problem is it's because it just gets to the process itself. It takes the numbers out of the way. It says, do you understand the freaking process? You always do the same damn thing. You should be able to do it with this because it's the same damn thing. You should be able to. It should be a little bit more comfortable now dealing with only letters. It shouldn't freak you out. Right? Now there are some little nuances here that I don't blame you for. How do you check if that's in the interval? We just talked about that. It's a true fraction. Yes, sir.
So the max would just be the...
Well, I don't know yet. When you plug this in, that's positive, right? Gotta be, because A and B are both positive. That's positive. So that to the A power is positive. How is that related to 1?
It's in between the interval.
So it's less than 1, isn't it? It can't be equal to 1, because A cannot equal A plus B. So 1 minus this is positive. To the B power is positive. So you get a number that is not 0. It's bigger than 0. So that is the location of your maximum. Both of these, the only other possible place that you could have a maximum, they're both 0. The other critical number you got makes this some positive number.
Do we know what A and B are? Or
No, we don't.
Did we just know that it's A over A plus B?
Yeah, all we know about them is that they're both positive. That's all we know.
Okay.
That's all we needed to know, and it just doesn't feel like enough when you start this problem. Yeah.
So the max would just be that X value.
The max would be F evaluated at A over A plus B. So just shove that dude in there, right?
Oh.
Who cares? What are you going to do with it? Shove it in there, you're done. I would love it if you simplified 1 minus that a little bit. That would be awesome. I'm desperately hoping you guys understand. I mean, the beautiful thing when you have a restricted domain and they're asking you for max and min, you just check the endpoints and the critical numbers. And you just step back and look who's the biggest, who's the smallest. It kicks so much ass. It's so much better than the number line. The number line is when they don't restrict the domain. And they just want to know, find all of the max. Oh, shit. Because you can have you can have a min that's bigger than a freaking max. So you can't just step back and say, those are the big ones, those must be the max. You can't do that. So you have to have the number line to help me figure out when is it really turning around.
So, would the actual point be a over a plus b, comma f of a plus b for the actual point for the max?
Well, figure out what that is.
Well, yeah, I'm just.
I'll leave
for the
that.
y val-
I gotta leave something for you guys to
For the
do.
y value.
Exactly.
Okay.
Yeah, the max value though would be whatever this is. Leave that. So they ask you for the max value. That would be it.
I have a silly question. Would it be intelligent to distribute the x of today into the 1 minus x?
Considering that this might be 3 trillion,
Absolutely.
you can't do it. I mean, you certainly can't put that in there unless these are the same. Does that make sense?
Yes.
If these are the same, that can go in. Does that make sense?
Yes.
I'll take that as a yes. From the rest of you guys? I don't know. Okay. All right, so for example, this old issue about somebody telling me that this equals this, that always, kills me. I might have written it down and you're like, that. You're like, what's wrong with that? Now, what is wrong with that, obviously?
Not taking
More
seven
operation.
of the four.
Yeah, I got 7 2s that I'm taking out. I'm taking a 2 out of each of these. So I should have 7 freaking 2s. That's what I meant by if these are the same, you could put it back in. Otherwise, you can't do shit, really. Unless you expand the left of them, what is left over. And oh my God, why?
You can't have a.
In the case that A is less than B, then no. Okay, that's enough of that. Yes, sir.
Can we do 45, same section?
We did that one. Is that the one? The 5e to the negative point?
Yeah, that's what you're at.
Yeah, we did that one earlier. Sorry about that. All right. Let's get into some new stuff here. Or some new stuff. Okay. All right. So last time we talked about how to find the maxes and the mins.
Yes.
And we used what these are this is the local maxes and mins. So they have the whole absolute one, but the local maxes and mins are more important generally because normally you have a function that doesn't have a restricted domain. You just want to know everything you can about it. And this involves what steps?
Taking a derivative.
You find f prime,
Set it to 0
set f prime to 0
to get the critical values.
to find critical numbers.
And you plug the critical numbers back into
And then this one we're going to formalize just a little bit. This is called use the first derivative test. Which is really just the number line and the pluses and minuses and all that kind of stuff. Right, that's the first derivative test. Just testing the first derivative to see where's it positive, negative. Then I can see if it's a min or a max. So if it was like this, what would this here be?
be an even decreasing.
Min.
So what's the function doing?
It'd be a maximum.
Or max, yes.
Why would it be a max? Because here the function is going,
It's increasing.
the function is going up, this is positive slope, and then it's coming down, so right in the middle must be a max. I love it. So of course this must be a min, because it's going down and then coming up from it. Of course if it's negative on both sides or positive on both sides, it's just somewhere it rested and then kept going. So it's not a max or a min. So critical numbers are something to find first. Now of course I kind of left something out here because it doesn't happen as often, but it could be where it's equal to 0 or undefined. Thank you.
Would both max and min be both equal or even derivatives or even powers? Because
No, they'd have to be roots from odd powers, because then odd degrees, because then it would change around. Right? Odd multiplicity changes around, even does not. Yeah.
So if you have an endpoint that appears to be your highest point, but it's undefined, do you set that as your max, or do you go for like the next highest
So the point, if it goes to infinity, that officially cannot be a max.
Well, if it's just like a little hole at an endpoint or something, but it's like higher up than everything else. No.
And the reason is, if you have like this,
Yeah.
then you have no max value. Because the minute you think you have it,
You don't.
you just cut. So you say it's there. Then just go halfway between that and the hole, and you can do that infinitely long.
Just go to
So
the next.
yeah.
Okay.
So there is no single number that matches that. It's actually a limiting process. So we just say, screw it, there would be no max.
All right.
So in this case, there'd be no max, and in this case, there'd be no max. Right? They sort of are the same thing in two different ways. So yeah, it's sort of like the God thing, push it down, and it's all localized in a way. Okay, how are we doing so far? Okay, sort of. Today we're gonna. So this is kind of old news. Today we're gonna focus on second derivative and what does it tell us? Yes, sir.
Curvature or how?
I like it. So let's investigate something here.
Stick with next week.
Sorry. So the first derivative, of course, tells us the slopes, the rate of change of the outputs. How are the outputs changing over time as you go along the x-axis? How are we doing so far? So the second derivative, what does it tell me about?
How fast
So we have the function, we have the first derivative, that's the slope. And f double prime. What does it tell me about the slope?
changes how fast it's changing.
How quickly the slope itself is changing. How are we doing? So if I just investigate this, there's my slope, and what's my slope doing?
Increasing.
It's decreasing, right? My slope was pretty big here, and now it's not as big, not as big, not as big. So the rate of change, I can at least say that it's definitely negative. It's getting smaller, isn't it? Is that cool? So if the slope here was 7, now it's maybe 3, 2, 0, right? And then it gets negative. How are we doing so far? So certainly as I turn around this little hill, oh crap, kind of missed it. My slope is getting less and less. Now at some point it stops getting less. It turns the corner. The slope itself turns the corner. And at what point does that happen? I just kind of drew over it. There. We talked about this point before. True. Let's not use that word yet. So we've talked about this before in a few different ways. There's somewhere that's the most negative slope. And it's somewhere in between here and there. Right? It's the most negative somewhere in there. So somewhere in there is the point where the second derivative equals 0, because it's not changing. It's kind of, the velocity goes to a point, and then it starts to go the other way. How are we doing so far? Okay, maybe. And then you keep going. And now what's happening to it here? My rate of change of slope. My slopes are negative, and then it's not as negative, and then it's 0, and then it's positive. So now my slopes are
Decreasing. Or there's increasing.
increasing. Cool? How we doing? So in black, I just want to make sure you guys are with me. In black is the function itself. In black is f. In purple are the tangent line representations. And then I'm talking about, I haven't drawn yet, I'm talking about the second derivative. And the second derivative deals with how quickly these slopes are changing. So it seems like if I have this shape, what can I say about the second derivative? How was the slope changing? It was getting bigger or smaller? Was it going up? Getting smaller. So here, the slope, the second derivative must be less than 0. How are we doing? So if I'm in my car, and I see a red light, and I hit on my brake, I'm still going forward, but my velocity is decreasing. My acceleration is negative. That's why my velocity is slowing down. My velocity is getting smaller. The change in my velocity is negative. When something gets smaller, the change in it is negative. How are we doing there? Is that cool? Yes, sir.
Is that for the whole arc right there, or is that just
Up until that special point that I'll go ahead and call it. It's called the inflection point, and that's where your slopes go from decreasing to increasing, or vice versa.
So whatever that negative point is, the x value there to the, where the slope reaches that 0 point, even though it's going upwards, it is a negative.
I like it. So this is the weird thing. When I throw the pen up in the air, the first thing you do in physics is you say, okay, what direction is the acceleration? And people say, well, it must be up. And if it was up, I would never get this back. I would hit the, if I had enough mass, it would go through and just keep going forever. So you would desperately not, try to let anything go, including ourselves. We'd have to have some, I don't know. So thankfully, the acceleration is down. Now the motion is up.
Yes.
But if the acceleration is in the same direction as the motion, my velocity should increase. But what's my velocity doing? It's constantly decreasing. So the acceleration, which in this case is the second derivative of the motion, must be negative. So and of course, if you did this, what shape does it make? It's almost a parabola. A parabola, a downward parabola, more importantly, right? You kind of with me? So that's exactly what this is saying. My second derivative is negative. It's pulling it down. So of course, when I have this shape, amazingly, my second derivative must be positive. I love it. And so right where these meet is right where it's changing. So that's the transition point. That's where it's 0.
So as the pen's going down, the velocity is, or the acceleration is increasing.
The acceleration is constant in that case, because it's just the acceleration of the Earth. That's a constant, yeah, in any given location, yeah. But the velocity is increasing in the negative direction, yeah. Okay, so what the hell does this mean for us? Now we can be a lot more precise in the shape when we connect the points that we find. So like in pre-calculus, I define all these points. Now you can find the maximum and the roots and all that old stuff. But now you can connect them with the right shape. And we call this one concave down. And we call this one concave up. It's crazy. So we call this cup down, cup up. If it holds water, it's up. If it doesn't hold water, it's down.
It's a sap base.
Or whatever liquid. Yeah.
So inflection points are just changes in concavity.
I love it. So what are maxes and mins, truly? How are they related to the function itself? Maxes and mins are locations where the function is going from increasing to decreasing. You with me? So inflection points are where the slope is going from, in this case it was decreasing to increasing. Are you with me? So in a very real sense, the second derivative's relationship to the first derivative is the same as the first derivative to the original function, of course. They're off by one derivative. Maybe. Okay. So.
That's not saying the second derivative is the same as the first derivative. The original function.
Second inverse, same as the first. So concavity. So we do this first. Then for concavity, I find the second derivative. And incredibly enough, I do what with it? Set equal to 0. Or undefined. To find, we still call them critical numbers, but they're the second derivative critical numbers. Because just like the first derivative, the critical number could be a true inflection point or not. It could just be a fake dude. It could be concavity's going to change. No, it ain't. How are we doing so far? Maybe a lot of similarities here with how those work. And then third, we do the same kind of thing to figure it out. Blah, blah. But here's another little thing. Here's the tie between these two. 3 star. In fact, let's do a specific example to show you what this 3 star is. Something's going to take the place of this, which is just awesome because this is normally a little bit, annoying to go through. Sure. So I'm going to do what I wanted to. I didn't do there. So what's f prime?
2x plus 2.
And what's f double prime? 2. Now, so f double prime is always Positive. It's not dependent on x. So this function is always concave up. And of course it is. It's a freaking parabola, right? That was the definition of the shape of cup up. So whatever the critical number is, because I know the value of the second derivative everywhere, more specifically at the critical number, since it's concave up, what must be true at the critical number? It must be a min. So if it's concave up at the critical number, it must be a min. If it's concave down at the critical number, it must be a... That's crazy. That's so much... Now, unfortunately, if the second derivative is 0 at the critical number, it's indeterminate. We have to use this first derivative test. You with me? But anything else, it's awesome. So it's really nice when it's constant everywhere. Then any critical number you find is going to be a min in this case. It's positive. Yeah?
Can you just repeat like what you just said about the concavity?
I don't know. If my critical numbers are x1, x2, and f double prime of x1 is negative, then x1, f of x1 is a what? So this would be down, so that must be a max. You guys with me? And f double prime of x2, let's say, is greater than 0, then x2, f of x2 must be a min. Yes, sir.
When you have a variable,
Local min.
when you have a variable in your double prime, you're going to evaluate your concavity based on
The critical number itself.
like numbers.
Say again?
Based on critical numbers for the first derivative then? I mean, you evaluate the
Exactly, I like it. So let's do one like that. So here, you guys take a minute and...
Double prime's like 2x instead of 2. And how you evaluate that concavity region.
Oh.
It's a 2 equals 0 factor.
Alright. Find the first derivative of critical numbers. And then find the second derivative. This, remarkably enough, this, what do you think its name is?
Critical number.
No. Second,
Derivative test.
that's amazing. Derivative test. Sometimes it's even spelled correctly, but you know, not every time. It's convention is to misspell it sometimes.
It's just that use the best.
Second derivative.
What is that CM? Is that
Critical number, yeah.
critical number? Okay.
Yeah. Not Cartoon Network. Critical. If your Cartoon Network is less than 0. Oh, that's kind of cool. Who's watching Cosmos?
Yes.
That's what it is.
It's so good. It's a little step in the right direction to try to get the masses to understand some stuff.
Carl Sagan shoots me.
Huh? Cosmos, yeah. It's on Fox and some other channels. I think it's National Geographic. Neil deGrasse Tyson. He's an astronomer. He was on the Daily Show a few times. That's where I first saw him. He's revived the old Carl Sagan Cosmos show with like stupid awesome graphics.
He's like an astrophysicist before.
Yes. Exactly.
Versus the Hayden bacteria.
So they literally can never run out of ideas for that show. I mean, if they did, it's like, let's all just die because we just figured everything out and explained it. All right, so what's f prime?
3x squared minus 4x.
I like it. So what are the critical numbers? What do you do here?
X away.
Good. So then,
0 and 4.
3x minus
so x equals
0.
0 and 4/3. Cool. Now we could do the number line right there.
Or
What's f double prime?
6x plus 6x.
Yep.
So what's f double prime of 0?
Negative 4.
Which is less than 0. So then what's happening at 0? So there's a max because it's concave down. Are you with me? It's almost too nice. It's a really nice marriage of the idea of concavity and max or min. If it's concave down, it must be a max there. That's the only possible turning point would be at the critical number. So max at 0, 0. Cool? And that's where you got to be really careful. When you're actually getting your points, you're finding your points through all these different derivatives. But if you want to find what the actual value is of the point, go back to the original function. And here you really almost can't go wrong, because it makes it 0. What's f double prime of 3/4? 4/3.
It's number.
4.
So the number?
Positive.
Yeah, mass is positive. Yeah, it's greater than 0. What is it? 284. Yay! So this will be a min at 4/3, comma something. Right? Just plug a 4/3 in there. How are we feeling about that?
Where do we plug in the 4/3 to?
Where do you plug in the 4/3 to? Original. So you say f of 4/3 and plug it in there.
Okay.
Cool. Yes, sir.
So for, why did you plug in the 0 for the f double prime?
Because that was one of my critical numbers.
Oh,
These are possible turning points. If they were not a turning point, what do you think would happen here?
Nothing.
What do you think this would be, this value? All right, let's try this. Could somebody give me a function? Very simple. What's the easiest function where the critical number is not a turning point?
Ln(x).
Y equals x. That's actually perfect. So that's a little too easy though, but we'll use it. But there's no critical number. There's x cubed. I like the way you think about it. It doesn't give me a critical number. X cubed, does it turn?
Kind of.
Yeah.
No. When I say turn, I mean going forward and now going backward.
Oh.
Going up, going down. It goes up, it rests, and it keeps going up. So it does not turn. It tricks us. Right? So what's f prime?
X squared.
So what's the critical number?
0.
0, right? That's the only critical number. It's the only thing that makes it 0 or undefined 0. What's f double prime?
6x.
6x. And what's f double prime at 0? 0. So the second derivative test is indeterminate. Now be careful. If it's not a true turning point, then the second derivative test will come out indeterminate.
Which means
If the second derivative test comes out indeterminate, it does not mean that that's not a turning point. I'll show you another example. Are you guys...
restate that.
If you get this, when you apply the second derivative test, you must go back and apply the first derivative test. Meaning, what does that mean again?
If it's turned on.
What's that derivative test?
Critical numbers.
Critical numbers, and do what with them?
See if it goes positive, negative.
Plot them and see what happens, right? Blah, 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 blah. How we doing?
Yes.
So of course here, all right, now this is neat. When I'm investigating, here's my 0. What am I going to plug 1 in to investigate that side? What am I investigating here? In fact, I mean, I pretty much tell you. You probably plug it into the first derivative. Because I'm looking at the slope, right? I want to see where the slope is up and down, to see where the max is mins. So at 1, the slope is, in fact, everywhere the slope, except at 0, the slope is positive, right? Because it's squared. So then I see that truly is not a turning point. Yes, sir?
If you have a higher power, what do the next derivatives do?
Exactly. So the example of where you have to be careful would be the next power up, x to the 4th. F prime is 4x cubed,
12x squared.
and then the critical number is
0.
0. F double prime is
12x squared.
F double prime at 0 is
0.
0. So you might say, oh, so then it's not a max or a min. It's just a turning point. But of course it's a min. We know what x to the 4th looks like. You with me? It's just that it's like a double trick, right? So I have to go back and do this. At 0, at 1, the derivative is positive. At -1, the derivative is negative. Therefore, that is a
Turning point.
turning point, a min, because it goes down and comes back up.
But you can also tell that.
Of course it is, because it's a freaking parabola. Right?
What the next
Yes, sir.
Yeah, you do the max min like time. find which one's the max and min for the first one.
Oh, here?
Yeah.
I did it using the second derivative test right there.
No, I mean like without that line thing.
I could do the line thing, or I could do this. Either way. Now, if I did the line thing, right, and these are both multiplicity 1. So I just have to know one thing. So if I look at 1, this is negative. Is that cool? So it's negative, positive, positive. It's going to change everywhere because it's multiplicity 1. So therefore, 0 is a... In fact, I can kind of draw this. It goes up, rests, not rests. It goes up, 0, goes down, 0, goes back up. So 0 is a max, max at 0. And of course, 4/3 is a min, min at that. You guys kind of with me? The only thing you lose is you can't draw this little rough sketch, but if all you need is this and that's where you're going to stop, screw the sketch. You just get to the answer. It's a little gamble because maybe you'll get something indeterminate that you got to go back. I mean, be careful. Well, that's still true. You can't determine the answer. So indeterminate, you got to go back and use the first derivative test, the number line. Yeah.
I have a question. To be indeterminate, does it have to be 0? F double prime of 0 equal to 0? Like F
Yes.
double prime 4 equal to 4, does it consider indeterminate?
No, because that's positive. Then it would be cup up, and then it would be a min. So 0 would be neither cup up or down, and the second derivative test can't tell what's going on there.
So why do we plug in the 0 to find that first derivative test?
Why did we plug that in?
Yeah.
Because it was the critical number. So if you find the critical number, that's where it might turn. If you look at the second derivative and it's concave up, it's a min. I mean, it's almost too simple to believe it's that simple.
Oh, okay, I'm trying to see, because that's a 4x cubed, that's why it's going to have a negative side, and the other side's going to be positive.
Yeah, because it's going to change signs on either side of the 0. Good.
And is that Z that it's changing signs on there, or is that
Sorry, say?
right there? Is that a Z?
That's a Z for 0, because a U would be undefined.
Okay.
So if we plug in 0, that makes it indeterminate. Let's just say we